In this video, we're going to learn yet another way to define our trig functions using a unit circle. And once we get to the entire unit circle on display here, I strongly suggest you memorize your unit circle because those are the values that come up the most often once you're in calculus and everything. So it comes in handy to memorize your unit circle so that you have all of your trig functions memorized for when you need them. So let's first talk about what we mean by a unit circle. So if we use a circle with radius r equals 1, centered at the origin, this is called the unit circle. Then our trig definitions simplify to, and I'm going to write them all down along with a picture of the circle that I'm talking about. So the trig definitions that we're going to rewrite are ones that involved x, y, and r from our previous video, but now we're going to use r equals 1 for all of those definitions. So let me just draw what's going on, and then we'll write down our definitions. So there's a circle. It has radius 1. So this is 1, 0, 0, 1, negative 1, 0, and 0, negative 1, and just pretend that's a perfect circle. I'm not the best at drawing circles, but imagine it's a perfectly drawn circle with radius 1. Then, if I have any particular point, pxy, on this circle, and t is that arc length there, then my sine of t, which we knew before was going to be y over r. Well, now r is just 1, so I just get sine of t is y. Cosine of t was x over r, so that's just x. My tangent t is going to be y over x still, provided x is not 0. Cosecant t is going to be 1 over y as long as y is not 0. Secant t is 1 over x, as long as x is not 0. And cotangent t is x over y, as long as y is not 0. So it's all of our same definitions from before. It's just everywhere we had an r before, we now just have a 1. And it makes our definitions a little bit simpler. And notice that this means that my p of xy is actually equal to the point cosine t, sine t. And we're going to be using that quite a bit. So let's do an example. Let's suppose that the real number t corresponds to the point p, which is square root of 5 over 5 to square root of 5 over 5 on the unit circle. Evaluate the 6 trig functions. Well, since I know this point is on my unit circle, I just need to use my new definitions. I know that sine of t is going to be my y value, which is 2 square root 5 over 5. And cosine t is going to be x. Well, that's square root 5 over 5. Tangent is going to be my y over my x. So I get 2 square root 5 over 5 over square root 5 over 5. And then I would have to flip and multiply by the reciprocal, and that gives me that tangent of t is equal to 2. So I found sine, cosine, and tangent, and now I just need to find my cosecant, my secant, and my cotangent. I know that cosecant is 1 over y, and so that gets me 5 over 2 square root 5, which if I rationalize the denominator, I get square root of 5 over 2. Either answer is acceptable. My secant is going to be 1 over my x, 5 over square root 5, which if you rationalize your denominator, you just get square root of 5. And then my cotangent is going to be x over y. So that gets me square root of 5 over 5 over 2 square root 5 over 5. And that simplifies to 1/2. And now I have all 6 trig functions using my definitions from the unit circle. All right, so let's take a look at what this unit circle looks like. In general, when people talk about memorizing their unit circle, they're talking about memorizing some very particular values on this circle. Let me draw a really big unit circle. So I have 1, 0. I have the point 0, 1, negative 1, 0, and 0, negative 1. So I know that this point here is corresponding to 0 or 2 pi for my angle. And we're going to put some of our special angles on here. I'm going to only put the radians, but you could also write this in degrees. I have pi over 6, pi over 4, and pi over 3. The points that give me cosine and then sine are going to be given by square root 3 over 2 and 1/2. So my cosine is square root 3 over 2 and my sine is 1/2. For pi over 4, I get square root of 2 over 2 for both sine and cosine. And for pi over 3, I have a 1/2 for my cosine, square root 3 over 2 for my sine. And so that gives me that first quadrant of the unit circle. And that's the most important one to memorize because all of the others can be found with symmetry. So this point up at the top is given by with the angle pi over 2. Just like I know this angle over here is pi, and this angle is 3 pi over 2. So all of the points give me cosine, comma, sine for that particular angle. And so let me just fill in the next bunch. My next group of angles, I have 2 pi over 3, I have 3 pi over 4, and I have 5 pi over 6. And the values over there, I just get to reflect across the y-axis the values that I had on the other side. So that's going to turn all my x's negative. My cosines are going to be negative, my sines are still positive, but the rest of it stays exactly the same. And then the same thing happens down here and over here. In this quadrant, both my sine and my cosine are going to be negative. And in this quadrant, my cosine is going to be positive and my sine is going to be negative. So just for the sake of completing up our unit circle, We have 7 pi over 6. We have 5 pi over 4. And we have 4 pi over 3. And I get to get these values by reflecting this quadrant across the x-axis, which makes all of the y's negative. So I'm going to have negative root 3 over 2, negative 1/2, negative root 2 over 2, negative root 2 over 2, and negative 1/2, negative square root 3 over 2. And we get to do the same thing in this last quadrant. I have my 3 angles, which I have 5 pi over 3, I have 7 pi over 4, and I have 11 pi over 6. And I can get the values for these points either by reflecting my original guys just across the x-axis or reflecting the ones I just did across the y-axis. Regardless, you're going to end up having positive x's, so positive cosine values, and then negative sine values. So I'm going to get 1/2 negative root 3 over 2, positive root 2 over 2, and negative root 2 over 2, positive root 3 over 2, and negative 1/2. And that completes the unit circle. That is what people usually talk about when they say memorize your unit circle. So you would be expected to know this before you finish your trig class, and definitely by the time you're in calculus. If you're a current student of mine, you can check on our course page and I'll have a unit circle posted up there. That doesn't mean you get to use that on exams or anything. You need to memorize it so that you have it in your head in order to use it on the exams. All right. So that is our unit circle. Now, using that, let's evaluate the 6 trig functions of t equals 5 pi over 6. Well, using my unit circle that we're supposed to get memorized, I can get sine and cosine. Sine of 5 pi over 6 is 1/2, and cosine of 5 pi over 6 is negative square root 3 over 2. Those were taken directly off of our unit circle. And now I can find my other functions just using these. Tangent of 5 pi over 6 is sine over cosine. So I get 1/2 over negative square root 3 over 2, which that simplifies to a negative 1 over the square root of 3. Then I can find my cosecant by remembering that cosecant is the same thing as 1 over sine. So my sine was 1/2, so cosecant is going to give me 2. My secant is going to be 1 over cosine, so I just have to flip this guy upside down and get negative 2 over square root of 3. And then my cotangent is 1 over tangent, so I can flip that guy upside down and get negative square root of 3. And there we have all of our 6 values. So once you have that unit circle memorized for your sine and cosine, you can get all the others just by examining different ratios. So we're going to step away from that for just a second to talk about the domain of our trig functions. Just notice, remember when we were defining these, some of our functions have us dividing by x or y, so we need to not have those values being 0 if we're evaluating that function. But now we need to think about when do those values equal 0 so that we can write the domain of all of our trig functions. Well, sine and cosine are going to be your favorites for these because if your function is sine of t, our domain is going to be all real numbers, negative infinity to positive infinity. Because my sine of t was just defined using that y value on our unit circle, so we had a y value for all of those. My cosine of t, similarly, has a domain of negative infinity to positive infinity, all real numbers, because my cosine was just my x value on the unit circle. But now we get the interesting ones. For tangent, remember tangent is sine over cosine. So it's going to be undefined every single time your cosine is 0. And your cosine is 0 when the x value of your unit circle is 0. So that's going to be on the y-axis. That's our pi over 2 and 3 pi over 2. And it keeps repeating the more times we go around. So I can have any value for my domain. So I'm going to say my domain is the set of all t as long as my t is not equal to 2n plus 1 times pi over 2, where n is an integer. Now, that's a really fancy way of saying my domain is every single number except for the odd multiples of pi over 2. So I can't use pi over 2, 3 pi over 2, 5 pi over 2, and so on. Now, similarly, if I look at cotangent, well, my domain is going to be the set of all t such that I'm not dividing by 0. Well, cotangent has the sine in the denominator. My sine is 0 exactly when my y value is 0. That was at an angle of 0 or of pi or 2 pi and so on, multiples of pi. So t cannot be n times pi, where n is an integer, meaning my domain is all of the real numbers except for multiples of pi. My secant and my cosecant are very, very similar to these. For my secant, remember secant is 1 over cosine. So I need my cosine to not be 0. So that's going to be just like my tangent's domain. I cannot have odd multiples of pi over 2. But every single other number is okay. And for my cosecant, my domain is all of the numbers except for multiples of pi. Because my cosecant is 1 over sine, and sine is 0 when I have a multiple of pi. So that's all of the domains of our trig functions. Example. Just evaluate the trig function. Our first one is going to be cotangent of pi over 2. Well, I know that cotangent of pi over 2 is going to be cosine of pi over 2 over sine of pi over 2. I could also just write this as x over y using my definitions from the unit circle. Now, regardless, pi over 2, we're talking about this angle up here. The x value of that point is 0, and the y value is 1. 0 over 1 is 0. So cotangent of pi over 2 is 0. Now let's try one with cosecant. What is the cosecant of negative 2 pi? Well, remember, our domain of cosecant is all of the real numbers except for multiples of pi. Well, negative 2 pi is a multiple of pi. So I know this is not in the domain, and that means this guy is undefined, just based on using our domain. Now let's have a definition that's very important when working with trig functions. A function f is called periodic if f of t plus p equals f of t for some constant p. And the smallest positive value p for which f is periodic is called the period of f. Now, all of our trig functions are periodic. So that means that they repeat values over and over again. And if you think about it, it makes sense because we've defined them based on this unit circle and we keep going around that circle over and over and over again. So you're going to get repeating values. Now, the question is, what are the periods of all of these trig functions? I'm going to write down some properties that show us what the periods are. Sine of t plus 2 pi is equal to just sine of t. And that means that my period is going to be 2 pi. Because when I add 2 pi to the argument of sine, I'm still going to get the same result that I would have had before. Same thing is true with cosine. Cosine of t plus 2 pi is just cosine of t. That period is also 2 pi. And as you can imagine, since our cosecant and our secant are defined using sine and cosine, we have that same exact property and period for both of these. Period is 2 pi for sine, cosine, cosecant, and secant. All of them have a period of 2 pi. But my tangent and my cotangent have a slightly different period. And that you can figure out by just looking at the values for all different angles. Just add different values to it. But I'll just give you the property and summarize what the period is for you. My tangent of t plus pi is equal to tangent of t. So the period of tangent is just pi instead of 2 pi. That just means the values for tangent repeat every pi rather than just every 2 pi. And same with cotangent. That period is also pi. Now, we can use the facts that we just wrote down, all those properties and knowing the periods of the trig functions. We can use those facts to evaluate trig functions. So for example, let's evaluate cosine of negative 7 pi over 3. Well, I know that the period of cosine is 2 pi. So if I add 2 pi inside of the parentheses, I'm not going to change the end result. So I know cosine of negative 7 pi over 3 is equal to cosine of negative 7 pi over 3 plus 2 pi, just using the period of cosine. Well, simplifying inside the parentheses, that gets me cosine of negative pi over 3. Now that's still not something I have memorized on my unit circle, but I know the period is still 2 pi, so let me do it again. Using that property, I know I can add another 2 pi inside the parentheses and still have the same end result. Simplifying within the parentheses gets me cosine of 5 pi over 3, which is a value on my unit circle. I get 1/2 for that result. Let's do another one. Tangent of 600 degrees. Well, this time we're using degrees instead of radians, and we learned that our tangent has a period of pi radians. Well, pi radians is the same thing as 180 degrees. So I know that I can have 180 degrees added inside the parentheses, and similarly, I can also subtract 180 degrees from that. But I want to subtract it as many times as I can possibly do all at once. Well, let's see here. I guess let's just take it one step at a time, just in case. I know I can subtract 180 degrees. That's one period for tangent. 600 minus 180 is equal to tangent of 420 degrees. And now I'm going to subtract another 180 degrees, trying to get it down to something I know from my unit circle. So doing that again, I'm going to have tangent of 420 degrees minus 180 degrees, and that ends up getting me tangent of 240 degrees. Now that is something that I can find on my unit circle. So 240 degrees, I'm just going to have to look at what the sine is and what the cosine is using my unit circle. And I get a negative square root 3 over 2 for my sine and a negative 1/2 for my cosine. And when I simplify that, we get square root of 3. So again, you can use the period of your trig functions by either adding or subtracting that period within the parentheses until you get to a value on your unit circle to make it easier to evaluate. So talking about our trig functions, we've learned that we have very particular domains for our trig functions, and we've learned our trig functions are periodic. And we have some other properties of our trig functions as well. Some of our trig functions are even, and some of them are odd. So sine of negative t is equal to negative sine of t. That's the same thing as saying our sine is an odd function, symmetric with respect to the origin. Cosine of negative t is equal to just cosine of t. That's the definition of an even function. That would be symmetric with respect to the y-axis. Cosecant of negative t is negative cosecant t. That is odd. Secant of negative t is just secant of t. That's even. And then I just have tangent and cotangent left. Tangent of negative t is negative tangent of t. That's odd. And cotangent negative t is negative cotangent of t. That is also odd. So of our 6 trig functions, 4 of them are odd and 2 of them are even. It's only cosine and secant that are even. The rest of them are odd. Now we can use those properties to simplify and evaluate different things involving our trig functions. So for example, let's simplify secant of theta minus 2 secant of negative theta. Well, using the fact that my secant is an even function, I know secant of negative theta is just going to be secant of theta. So I can rewrite this as secant theta minus 2 secant of theta. This was because it was even. And now I have like terms, and we can combine them together to get a negative secant of theta. Let's do another one, simplifying using the even or odd properties. Sine of 2t plus 2 pi minus sine of negative 2t. And I want to simplify this. Well, first, let's look at this first sine. It says sine of 2t plus 2 pi. But we know that the period of sine is 2 pi. So sine of anything plus 2 pi, that's just going to be that sine of 2t. So what I used on that line is the period of sine. Now look at the sine of negative 2t. I know sine's an odd function, so I can take that negative and I can rewrite this as a negative sine of positive 2t. That would change this to plus sine of 2t. That's because we have an odd function. And now I have like terms and can combine them together to get 2 sine of 2t. All right, and let's just do one last example to wrap up this video. For a given real number t, express tangent of t in terms of secant of t. And now that kind of sounds a little scary because we don't really know what to do to start. But one thing we do know is we have our unit circle and we have things to find using a unit circle. The equation of our unit circle is x squared plus y squared is 1. That's a circle that has a radius of 1 centered at the origin. And now I know from my unit circle, x is equal to cosine of t, and y is equal to sine of t. So cosine squared t plus sine squared t is equal to 1. And let's look at what they want us to find in this problem. I have a tangent and I have a secant. I know that tangent is sine over cosine. So let me just divide everything by cosine squared t so that this guy ends up being a sine squared over a cosine squared. So I can rewrite it as tangent. So if I divide everything by cosine squared t, and then simplify, cosine squared t over cosine squared t is 1. The sine squared over cosine squared is tangent squared. 1 over cosine squared is secant squared. Well, now this is good news because I've rewritten my unit circle equation so that it has tangents and secants in it. And our goal on this problem is to write tangent of t in terms of secant of t. So let's just solve this equation for tangent of t. I can subtract 1 from both sides. And then I can take a square root. And I get tangent of t is equal to plus or minus a square root of secant squared t minus 1. And now I have tangent written in terms of secant. Now notice we could have taken some shortcuts if we remembered some of our Pythagorean identities, because we end up with one of our Pythagorean identities along the way in this process. But this was using just the unit circle definition since the video was based on unit circle trigonometry. And that's all I have for you on this video. If you have any questions, feel free to drop them below. If you're a current student, you can also ask through email or office hours or in class. And in our next video, we're going to talk about how to graph all of our trig functions, as in graphing the function and not just putting a unit circle on a piece of paper. So stay tuned for that. I'll see you guys next time.